In our modern world, technology is all around us, keeping us moving, powering our cities, and even taking us off the planet. Our lives rely on this technology operating healthily every day. We all take it for granted that doctors and nurses are there to help us stay healthy, but have you ever stopped to think who looks after the health of a plane, a train, or a bridge? If you break a bone, doctors will do an X-ray to find out where you've broken it and how badly. During pregnancy, doctors will see the baby before it is born using ultrasound. These same techniques are regularly used by engineers to discover the health of large and small structures. This is the science of non-destructive testing, or NDT for short. We send signals into the material and analyse the echoes that we receive back, and use this to determine what caused the echo and where the echo originated from. For us engineers, our patients present particular challenges, and they include
an oil and gas pipeline. This transports vital resources across the world, including deep under the ocean.
Part of a nuclear power station, it will be located in a highly radioactive environment.
Fan blades in a jet engine. There are hundreds of them in an aircraft, and they experience extreme temperature changes.
We're looking for things that weaken a structure or component so that it's likely to fail. These things can be cracks or inclusions, which we call defects. Some will occur during manufacture, whereas others will develop over the lifetime of the structure. Take the Clifton Suspension Bridge in Bristol as an example. It needs its health checking as it was built in 1864, which is 20 years before the first car, and is now crossed daily by thousands of motor vehicles. This means that cracks might form due to the constant traffic and wind loading on the bridge. The good news is that the bridge was over-designed, and so it's very resistant to defects and cracking. And also the forces on the various components have been thoroughly analysed, and so the weak points have been located. That means that we only need to test it in a few locations. When inspecting components on the bridge, we're looking for very small defects. These can be hidden from our scanners by the very material the defect is located in. In our engineering lab, we are working on improving techniques to make the best possible diagnoses of our patients.
NDT is used during the manufacturing of the majority of components of a nuclear power station, such as this graphite core, which holds the nuclear fuel rods. NDT is used to ensure the quality of components, because after installation, access is virtually impossible. One technique used is ultrasound.
X-ray computed tomography allows us to visualize the internal structures of a component in 3D. Instead of firing sound waves, we fire electromagnetic waves in order to produce images based on the interaction of X-rays with matter. We can visualize the internal structure of complex parts using X-ray computed tomography. We can reach very high resolutions, smaller than the width of a human hair.
Throughout NDT, we use simulation to predict the interaction with structures and to understand experimental results from real components. We build up accurate computer models of expensive components, which reduces cost and allows us to build up a virtual defect database. In this model of the pipe that we saw earlier, we've introduced a virtual crack into our simulation. We can see the sound waves travelling along the pipe and being reflected from the crack in the centre.
There are engineers and scientists all across the country working daily to prevent disaster. By looking deep into the structures that make up the modern world, they keep us safe and sound. These people are the unsung heroes of engineering.